Hello, my name is Holly Batchelder, and today we'll be talking about Project 1, how to decipher a Hill-Cipher using Gauss-Jordan elimination and Module 26. Okay, so as you can see here on the screen, we have our encrypted message and we have our encryption key. So the encryption key is going to be rewritten into a block matrix, okay? It is going to be rewritten, for instance, in this case, in a 3x3 matrix. This will allow us to do further calculations on this matrix and also allow us to find the inverse of it. Now, the encrypted message, rather, will be written into vectors. So since the encryption key has 3 rows, the encrypted message vectors must have 3 rows, which is why we have 4 vectors. Okay, so they are all 3, 1 matrices, or you could consider them vectors as well. Okay, so now that we understand that, the next thing that we're going to do is convert these letters into numbers. So for the Hill-Cipher is actually very convenient. The trick here is each letter corresponds to a position in the alphabet, and that position is given a number. So for instance, A is 0, B is 1, C is 2, and so on. Okay, so for our encryption key, this is going to equal 2, 8, 15, 7, 4, 17, 8, 13, and 6. And our vectors will be converted into 23, 17, 2, 10, 23, and 8, 17, 3, and 6, and finally 12, 14, and 23. Okay, so since these are all converted into numbers, this will allow us to do calculations. Eventually, we will have to multiply these two guys together. So by having it in number forms, we are now all prepared to start our Gauss-Jordan elimination and begin deciphering the matrix. Okay, so Gauss-Jordan elimination, the way it works is we set up our matrix that we want to find the inverse of. So if we go back up to the top, the cipher matrix, the key matrix, the encryption matrix, which is this one, which we translated over to here, right? Into numbers. This is the original matrix. We want to find the inverse of it. We need the inverse so that way we can decipher the message. So the way we're going to do this is with Gauss-Jordan elimination. The original matrix, which was the key matrix, is going to be on the left, and it is going to be set up against an identity matrix. Okay, so the beauty of the Gauss-Jordan elimination is any operation that you do on the original matrix will be done on the identity matrix. So eventually you will see that those operations will convert the left side into an identity matrix and the right side into our inverse matrix. Okay, so for our steps, first we're going to identify our pivot. Our first pivot is 2. We are going to eliminate 7 and 8. So for those positions at 2, 1, our multiplier is going to be 7 over 2. Our position at 3, 1, our multiplier is 4, leading to the row operations of R2 minus R1 times, R2 minus 7 over 2 R1, and R3 is going to turn into R3 minus 4R1. Okay, so if we conduct these row operations, which I'm not going to go through in front of you, that will take very long, you will get this as the resultant matrix. So now we're going to continue along our path. The goal of what we're doing right now is to reduce this into an upper matrix form. So now we have to eliminate 19. So our second pivot that's going to help us with that is negative 24. Our multiplier is 3, 2 position will be 19 divided by 24, and the row operation will be R3 minus 19 over 24 times R2. Okay? So now after completing those operations, the singular operation on row 3, we will be finally in the upper matrix form. We have our zeros down here, which is perfect. That's what we want. Those are our zeros, right? And now we are going to convert this into a diagonal matrix. Okay, so how to do that? We have to eliminate 8, 15, and negative 71 over 2. So let's first start with 15 and negative 71 over 2. So our pivot that's going to help us with that is our third pivot, right? Is negative 1243 over 48. And we are eliminating positions 2, 3. So our multiplier for 2, 3 will be 1704 over 1243, excuse me. And we are also eliminating positions 1, 3, which is negative 720 over 1243. So these row operations will be R2 minus 1704 11240 over 11243 times R3. For R1, our row operation will be R1 plus 720 over 11243 times R3. Okay, so we conduct those row operations, we get this resultant matrix. Don't want to spoil the punchline down there. Okay, so we have our resultant matrix here after conducting those 2 row operations. As you can see, we got these 2 reduced into 0, perfect, and now we need to reduce 8 into 0. So our final row operation to get this into a diagonal form, we will be using the second pivot, which is negative 24. Our multiplier for the position 1, 2, since that is the one we want to eliminate, will be 1/3, negative 1/3. So we write that. And the row operation there is R1 plus 1/3 R2. Okay, and if we complete that row operation, we are going to finally get our diagonal matrix, right? Where we have just the diagonal values. And notice those diagonal values are our pivots. Those pivots did not change at all while we were doing our row operations. So a note to yourself is if those pivot values do change, you've done something wrong. Also, keep in mind, since these numbers are quite large and honestly kind of obnoxious the way they're really huge denominators, it's going to get tricky sometimes with those row operations, so I definitely recommend using MATLAB so that way there are no errors in your calculation for your inverse matrix. If there's an error, then your whole inverse matrix will be wrong and you will not be able to decipher the matrix. Okay, great. So now that we have this in a diagonal form, now we need to reduce these diagonal values into 1. Okay, so how are we going to do that? Each row is going to have its own specific operation. So row 1 is going to be multiplied by 1/2. Row 2 is going to be multiplied by negative 1/24, 1 over 24, excuse me. And row 3 is going to be multiplied by negative 48 over 1243. Now remember, we have to convert it into a positive 1. That is why some of these values are negative. And if we use these row operations that we have written right here, we will get our identity matrix on the left and our inverse matrix on the right. So now we have completed the Gauss-Jordan elimination. We have got the information that we want, and we are all set to continue on with this deciphering. Okay, so next step is let's just take a look at this right side of our Gauss-Jordan elimination system. Notice that we have a common denominator, right? We have a common denominator of 1243. meaning that we can take out 1 over 1243 because that's a common factor. By taking that number out, 1 over 11243, excuse me, is going to be our determinant, okay? And our determinant can be placed outside the inverse matrix. So let's just take a look at what that all looks like. We take that determinant out. Our inverse matrix is now this. 1 over 11243, and all those values that were up in the matrix that we had just solved, those is the same number, just without the denominator, right? Okay, great. So now we have finally got our inverse matrix in the proper format. We have our determinant. Everything is great. Okay, so what's the next step, right? The next step we're going to do involves the determinant and mod 26. Okay, so mod 26 is extremely useful here and extremely important because the mod 26 allows us to map numbers that are outside the range of 0 to 26 back to the range of 0 to 26, right? So since only the alphabet goes to 26 and those are the only numbers we can work with to decipher a matrix, we have to be able to map back to that. So numbers like 147, that's not going to help us because there is no 147th letter in the alphabet. So how are we going to fix this? What are we going to do? Well, we use the mod 26. Okay, so let's figure out what the corresponding mod 26 value is for here. So we have our 1 over 112, 43, equaling some mod value of 26, right? Okay, so how are we going to figure this out? Well, there are some properties of the mod that are very helpful to know. If you multiply each side by the same scalar multiple, that is allowed, that will work. So kind of going back to basic algebra, but it also applies to the mod 26. So then if we do that, we can rewrite this as 1. And we're going to switch that question mark into something a little bit more mathematical. We'll call it x for that variable of 26. Okay, so that's our new format. It's easier to work with. We don't have to work with a fraction. And another property of the mod 26 is you can alternate and flip these values. So we're going to flip 1243x with 1 onto the other side. So we have this resultant equation. All right. So now we're all set up to solve for this mod 26. And it's important to note that this side is going to be your dividend. And here is going to be our remainder. And the 26 is our divisor. So basically how you manually solve for the mod 26 is through long division. So yeah, it's through long division and we want the remainder of 1. So what value times 1243 divided by 26 will get the remainder of 1? There's only a couple ways to figure this out, and we're going to use for our manual method, the hit and trial method. So let's test out x equals 1. The good thing about this, even though we have to go through a bunch of numbers, is you can only go up to 26. You only have the range of 0 to 26. But we're going to start with 1. So if we put 1 in for x, then that would mean 1243 times 1 is 1243 is going to be divided by 26. And just so we don't have to go through all the long division on here, I'll just tell you the answer. It's going to be 47 with a remainder of 21. The remainder of 21 is not a remainder of 1. So x is not our 1 is not our answer for x. So we can continue going through x equals 2, x equals 3, and so on. But let's just cut right to the chase. The correct answer is going to be x equals 5. Okay, so the way that one looks is, let's just take a look at it. It's going to be 26 divided by 5 times 1243, which equals 6215. If you divide that, you're going to get 239 with a remainder of 1. So since we have that remainder of 1, we have the remainder of 1, remainder of 1, that's what we wanted. So now we know that 5 is the correct answer for X. Okay, so let's put 5 back in there. So if we have 1243 times 5 and mod 26, right, with the remainder of 1. Well, let's just backtrack. Remember, we started with a fraction, 1 over 1243, and we need to get back there because that's our real determinant. So let's just divide the whole thing. Remember, we can do this with our scalar multiple. You can do a scalar multiple of a fraction. So 1 over 1243, multiply both sides, 1 over 1243. These cancel, and we get 5, 1 over 1243 mod 26. And remember our old principle, our old property that we use, you can flip these guys and you will get 1 over 1243. 5 is the number that solves this mod. Okay, so now we know 5 is the multiple of mod 26, so that we get 1 over 1243. Great, so that is very important. All right, so what next? We figured out the mod, we figured out what the value is to make this mod work for 1 over 1243. Now we're going to put it to use. So what we're going to do is we're going to substitute out, let me phrase that. We're going to multiply the inverse matrix by 5 because that's the number that satisfies mod 26 for 1 over 1243. So here we are. This is how you'd set it up. We have our inverse matrix times by 5. And for this, each number gets multiplied by 5. So we will get this as the following resultant matrix. Okay, great. So that's our resultant matrix. And then what we're going to do is for each one of these values, we are going to take the mod 26 of them. So just like how we did before, it would be long division again, but instead I'm not going to use long division. I decided to use MATLAB on this one. It's a lot easier, a lot quicker, ensures the correct answer. So the way you would code for this in MATLAB would be the following: mod, let's just do the first one here, mod negative 985 comma 26, because this is the mod 26, and you would get a number. The answer is 3. So that's the remainder, right? 3 is the remainder. Okay, so you do this for each number in this matrix, and then you just take the answer that you got and just substitute it right back into that position. So since we know that's 3, let's just, you'd go through each number, right? And you would get the resultant matrix of 3, 7, 16, 2, 6, 17, 9, 8, and 20. And this is your decrypted key, right? Because we did all the Gauss-Jordan elimination, we got the inverse, we figured out the mod, how to map it back to the numbers, or excuse me, to the letters. So this is our decrypted key. Yay, okay, we are almost there. So the next step, remember like all that way back ago where we had our decrypted message? Well, now that's coming back. So our decrypted message, we had like a bunch, not a bunch, but we had 4 vectors, right, of that decrypted message. It was 23, 17, 2, then the next vector was, I'm reading it here, then the next vector was 12, 23, 8, and so on down the line, where we also had 17, 3, and 20, and then we also had 12, 14, and 23. Those were all of our decrypted vectors that we had calculated previously up at the very top, the very beginning of our video. So now, since we have our decrypted vector, we're just gonna, or excuse me, our decrypted key, we are going to multiply it by our encrypted vectors. I think I misspoke earlier. These, what I highlighted in yellow, are encrypted vectors. They are not decrypted yet. They are encrypted vectors, right? Okay. So we have our decrypted vector. Oh, goodness, sorry. Our decrypted key multiplied by our encrypted vectors. Right? Okay, that's what we're trying to do. Okay, so if we multiply each one, remember when you multiply, you will just get a vector here. So you're going to get 220, 182, 383. Okay, and so on down the line. If we continue, we'll keep going. So you might notice it's like, well, we just used the mod to get to numbers that are in the alphabet, and now we are way outside the alphabet with numbers such as 434. So what the heck? I thought we did all this work, so we were back in the alphabet, and now we are outside the alphabet. Yes, we are. But that's okay. We just have one more step after this, and I bet you can predict what that is, to convert these huge numbers back into the range of 0 to 26. The last one, 502, 499, and 680. Okay. All right, so that last step, let's scroll up to get to the first one. We are going to take the mod of these numbers, right? So just like how we did earlier up at the top, or not up at the top, but earlier to get the decrypted key, we're just going to take mod. So if this was a math lab, mod of 220, 26, and you get a value, right? For this one, we get a value of 12. That's the remainder, and that is the number that we want, so that way we can map it back to the alphabet. Okay, so if we went through each one and we did the mod calculation for each one, we would get 12, 0, 19, 7, 8, 18, 12, 24, 11, and 8, 5, and 4. Okay. So that's when you do the mod. 26 for each one, right? Okay, so now that we did our mod 26, we finally have numbers back in the alphabet. We are so close to being done. The last step is just translating numbers into letters. So that's just how their lineup is on the alphabet. So we have 12 is going to be M, 0 is A, T, H, I, S, M, Y, L, I, F, E. And for the final reveal, in case it's hard to look at the words vertically and all together, our message was math is my life. Okay, so that concludes this video. Thank you so much for watching and see you soon.